Take a look at this handwritten digit. It's clearly a 7, right? Our brains do this instantly, effortlessly. But what does it actually mean for a computer to recognize the 7? How does it go from a jumble of pixels to the confident declaration, "That's a 7"? This isn't just a parlor trick.
It's the foundational problem behind everything from reading checks, to self-driving cars identifying stop signs, to medical imaging analysis. It's about teaching machines to see and understand. In this series, Training and Data, we're diving deep into the core mechanics of how AI systems learn.
We're not just showing you what they do, but how they do it, piece by painstaking piece. Today, we're building the very first conceptual blocks of a neural network, starting with that handwritten 7. So, let's start with what a computer actually sees when it looks at our 7.
It doesn't see a graceful curve or a sharp angle. It sees numbers. Imagine this 7 is drawn on a tiny 28 by 28 pixel canvas. That's 784 individual pixels. Each pixel is just a number, representing its brightness. 0 for black, 1 for white, and shades of gray in between.
So, our 7 is just a list of 784 numbers. How do we turn these numbers into a decision? How do we get the computer to say this is a 7 and not this is a 1? Let's simplify drastically. Imagine we want to detect any vertical line.
How would you, by hand, check if a small image contains a vertical line? You'd probably look for a column of bright pixels. If the pixels in the middle column are bright, and the surrounding ones are dark, you'd say yes, vertical line. A computer does something similar, but with numbers.
It uses what we call weights. Think of weights as a set of preferences or filters. For our vertical line detector, we'd want to give high importance to the middle pixels, and low, or even negative, importance to the side pixels.
We multiply each input pixel's brightness by its corresponding weight. Then, we sum up all these products. If the sum is high, it means the input strongly matches our vertical line pattern. If it's low, or even negative, it doesn't. This sum is our first step towards a decision.
But why do we need a bias? Imagine our vertical line detector. What if the image is just completely black? All input pixels are 0. Our sum would always be 0, no matter the weights. A bias is just an extra number we add to our sum after all the multiplications.
It allows us to shift the entire result up or down, making it easier or harder to activate our detector, regardless of the input. It's like a baseline level of enthusiasm. So, for one tiny neuron, our basic decision unit, the process is, multiply inputs by weights, sum them up, and add a bias.
This gives us a single number. But this single number isn't quite a yes or no yet. It could be any value, positive or negative.
We need to squish it into a more useful range, like between 0 and 1, where 0 means definitely no, and 1 means definitely yes. This squishing function is called an activation function.
It introduces nonlinearity, allowing our network to learn more complex patterns than just straight lines. For now, think of it as a way to turn our raw sum into a probability or a clear on or off signal.
So, one neuron takes many inputs, multiplies them by its unique set of weights, adds a bias, and then passes the result through an activation function to produce a single output. This output can then become an input for other neurons.
Now, imagine we have not just one neuron, but many, arranged in layers. Our 784 pixel values from the 7 image become the inputs to the first layer of neurons. Each neuron in this first layer will learn to detect a different simple feature.
One might look for horizontal lines, another for diagonal edges, another for curves. The outputs of these first layer neurons then become the inputs for the next layer of neurons. This is where the magic starts to happen. Why multiple layers?
Because combining simple features allows us to detect more complex ones. A neuron in the second layer might combine a horizontal line and a vertical line to detect a corner, or combine several curves to detect a loop. By stacking layers, our network builds a hierarchy of understanding.
From raw pixels, to simple edges, to complex shapes, and eventually, to entire digits. Finally, we reach the output layer. For our digit recognition task, we need 10 output neurons, one for each digit from 0 to 9.
Each of these output neurons will give us a number between 0 and 1, representing the network's confidence that the input image is that specific digit.
The neuron with the highest value is the network's guess. So, when our handwritten 7 enters the network, it activates a specific pattern of weights and biases across all these layers.
This pattern ultimately leads the 7 output neuron to light up the brightest, telling us, yes, this is a 7. This is the fundamental architecture of a feed-forward neural network. It's a system of interconnected, simple decision-making units, working together to identify complex patterns.
Here's what we've learned today. 1. Computers see images as numbers, specifically pixel brightness values. 2. A neuron is a basic decision unit that combines inputs using weights and a bias, then processes the result with an activation function. 3.
Neural networks stack these neurons in layers, building a hierarchy